Thank
Sayla.
you.
Thank you. And our next speaker will be Deyi Xiong. Is Deyi here? Oh, great. Hello, Deyi. Welcome to the workshop. So Deyi is our next speaker. Deyi is a professor of computer science at Tianjin University in China. And there he's the director of the NLP lab at the College of Intelligence and Computing and of the International Joint Research Center of Language Intelligence and Technology. Before joining Tianjin University, he was a professor at Suzhou University and a research scientist at the Institute for Infocom Research in Singapore. His research focuses on NLP, specifically machine translation, dialogue, natural language generation, and common sense reasoning. He has published an enormous number of papers in top NLP conferences and journals, and he's one of the leading researchers when it comes to modeling discourse and similar difficult phenomena in machine translation. So I'm really excited that he agreed to speak at our workshop today. Deyi's talk today will be about modeling cohesion devices for context-aware neural machine translation. So please, Deyi, go ahead. Thank you.
Okay, good morning. Thank you, Christian, for having me here. So today I'm going to present our recent efforts to document-enabled machine translation. So can you hear me? It's okay.
Yes, I can hear you.
Okay, great. So I use the title of our first work to present this talk, but actually we also include other work on dialogue translation. So before we present our findings, let's look at a Chinese English machine translation example. So this is a very long sentence in Chinese, and maybe you don't understand Chinese, but if you look at this is a Google translation, it's a recent Google translation. So we can see a lot of problems. First, we can see the verb is not translated in, consistently in terms of the tense. And also there is a big problem in the last sentence. Actually, it's not a sentence, just a word. So how this happens? This is because there is a huge difference between Chinese discourse structure and English discourse structure. In Chinese, a long sentence usually composed of several short clauses, and these clauses are separated by commas, and all these clauses share the same subject. But usually, the first class will show the subject, and the following classes will omit this subject. So this Chinese, because Chinese is a ProDrop language. But if you translate this long sentence into English, it has to be multiple English sentences with subjects. So this has a problem for sentence-level machine translation. Okay, so this just one problem to Chinese English translation. We also see a lot of other problems related to discourse phenomenon. So for document-enabled machine translation, actually we are confronting many different challenges and the problems. For example, wide context and the lack of document-enabled training data and the lack of automatic evaluation matrix, just mentioned by Sayla. Actually, it's very difficult to maybe for human beings to evaluate document-enabled machine translation. So it's more difficult for machine to evaluate the quality of document-enabled translation. So our recent efforts are trying to focus on these first three issues. These three issues are very, very challenging. So we just try to to alleviate these issues to some extent. Okay, so this we are going to the first work. This is a new machine translation, document-enabled translation framework we call CoDoNMT, focus on modeling cohesion devices for document-enabled neural machine translation. And this work just has been accepted by CoDM in 2022. Okay, so what is cohesion? Semantic connections between words. So let's look at this example. The Amy and she actually force some connections of these two sentences. And there are important concept about cohesion is cohesion devices. These devices are important linguistic atoms that change sentences into cohesive discourse. So From the linguistic perspective, there are two groups cohesion devices. The first one is lexical cohesion devices that include reiteration, synonym, super-subordinate, and the second group is grammatical cohesion devices that include coreference, ellipsis, and conjunction. So in this work, we focus on the lexical cohesion devices and the coreference, and we leave these two issues to our future work. So I just briefly review these cohesion devices. Reiteration means the repetition of the same words in the discourse. For example, like the apple here in the first sentence and second sentence. And the synonym refers to atoms with similar meaning. And in this example, like the beautiful and the attractive. And the subordinate and subordinate are formed by words with an either semantic relationship. So let's look at this example. We are discussing Jack's furniture. I like his wardrobe very much. Wardrobe is kind of a furniture. So these two words form a subordinate relationship to connect these two sentences. Okay, for coreference as a relationship between two words in which both refer to the same thing and one is a linguistic antecedent of the other. So like the Amy and the she here is a coreference relationship. So we use external resources to detect these cohesion devices in document, and then we model and integrate them into the document level machine translation. The basic idea is just we want actually inspired by mask language modeling. We try to mask these cohesion devices in the current sentence to be translated, and then we force the decoder, force the model to predict these mask cohesion devices with context information. So in this way, we teach the model to learn how to use this context information. So basically, in the entire model, we have two essential components. The first one is a cohesion device masking. The second one is cohesion attention focusing. So these two components are all used in the transformer encoder. And we actually concatenate the preceding context with the current sentence together and import this concatenated sequence into the encoder. And we mask cohesion devices in the current sentence. And we use a multitask learning fashion to force the model to predict the mask token. And also we use the cohesion attention focusing in the self-attention layers. So I will introduce these two components one by one. So for the first component, cohesion device masking, the basic idea behind this component actually is to teach the model to learn to predict the mask token from the context. For example, like this one, this is the preceding context, and this is the current sentence to be translated. And there is a reiteration cohesion devices here, the dog. So we mask the dog in the current sentence and force the model to predict the dog from its context. And also this is a coreference cohesion relation. So we mask the pronoun he and force the model to predict these pronouns from the context. Okay, so this mask token prediction loss. This M means mask token, and the X apostrophe is mask version of the current sentence X, and the CX is the preceding context of X. Okay, so for the second component is about cohesion attention focusing. So for this component, we actually want the encoder to focus the attention to those useful words for the current sentence translation. Maybe you know that not all words in the preceding context are useful for a current sentence translation. So if you attend to all these words, maybe some are lousy for the current sentence translation. So in this way, we just want the encoder to just look at the cohesion devices. So this kind of motivation for this component. So how do we do this? We actually use 2 steps. The first step is we construct a cohesion attention mask. And then in the second step, we use this cohesion attention masks in the self-attention layer, in the decoder, in the encoder. So let's look at the first step, the cohesion attention mask. Basically, this mask is the matrix and is used to teach the model to attend the cohesion devices. So let's look at this example. This is the preceding context, and this is the current sentence to be translated. And then we can see the driving here forms a reiteration relation, and ourselves and we forms a co-reference relationship. So for the driving and ourselves, we want to them attend to a preceding context, but not all words, just pretend to attend the cohesion device, like the driving attended to the driving here. So other words in this sentence are all invisible to driving, but only the driving here are visible to this word. This is similar for the ourselves. So this attention mask actually use some visible tokens and invisible tokens to teach the current sentence how to attend to preceding context. Okay, in the second step, we after we have this constructing this attention focusing mask, we use this attention mask on the self-attention layer of the encoder. But as we think that this strategy may be too strict for the encoder, because sometimes there's some other words in the preceding context may be useful for the current sentence translation, not only the cohesion devices. So we decide to let the encoder to determine whether to use the cohesion attention mask. So we use actually use the probability threshold. So for each self-attention layer, we sample a variable epsilon. If epsilon is larger than the probability threshold, we then use this cohesion attention focusing mask. Otherwise, we do not use it, this mask. So that means we let the encoder to attend to any words in preceding context for the current sentence. Okay, in this work, we also found a serious problem in document-level translation. That's the exposure bias caused by the inconsistency between the training procedure and the inference procedure. Because in the training procedure, we use the ground truth target context, while in the inference, we use the previously decoded output. So to alleviate these issues, we just follow previous work, use the probability PO to control whether to replace the ground truth word with a machine predict word during training. So this is basically what we do. Okay, so now in this multitask learning framework, we have 2 tasks. One is primary task for machine translation, and the other one is a mask prediction task. So this is the loss for the machine translation. As we contacted the preceding context and the current sentence into the encoder, so we have the also we have a machine predict tokens in the target translation. So that is the Y poststory, and this X poststory is the mask version of the current sentence, and this is the context of the the source sentence, and this is the context of the target sentence. And we try to combine these 2 losses with hyperparameter lambda. So we conduct an experiment to compare previous work on document-level machine translation like HAND and CADEC. And this blue results show that our method can achieve substantial improvements over previous works. We also conducted linguistic evaluation using the contrastive test set from this, I think, from this paper. So we can see we have achieved a substantial improvement in the diathesis and the lexical cohesion. And we also conduct a Bayesian study to investigate the effectiveness of these two components. First, for the CoDM, we actually compare this kind of is a mask prediction on the Cohesion device, but we also can randomly masking words in the current sentence. So we compare our CoDM with a random masking. So we can see from, if you look at the blue score, actually there's no difference between this random masking and the Cohesion device masking. But if you look at the linguistic evaluation matrix, we can see our component can have a very significant improvements over the random masking. So that I think that this blue is not sensitive to the discourse phenomenon. This actually we can find many times in previous work on this. Okay, for the Cohesion Attention Focusing, actually we investigate the impact of the property threshold PM on the performance. Actually, this hyperparameter is kind of a variable to control the balance between attending to any words in preceding context and attending to only Cohesion devices. So we can see actually too high or too low of this property threshold will drop the performance. We can see here is a good value for the PM to achieve a basic performance on 3 test sets. Okay, so that's basically the conclusion of the first work. It means that Cohesion device actually is very important for document-enabled translation. If we can find a way to model these Cohesion devices, it actually can achieve some improvements on document-enabled machine translation. Okay, so let's look at the second work. This work actually is about a dialogue machine translation. We also follow a multitask learning framework. But our main interest in this work is try to improve the robustness of dialogue machine translation with context. So this is a joint work with ByteDance and Suzhou University, and is published in NICO 2021. Okay, so first look at the challenge of dialogue translation. We actually lack of the training data and benchmark tests for dialogue translation. And we also don't know what kind of translation errors frequently occur in dialogue machine translation. So in this work, we analyze dialogue translation corpus to understand these frequent translation errors. And we also generate contextual perturbation data to solve the problem of lack of training data. We also propose a multitask learning framework for dialogue translation to improve the translation quality of dialogue translation. And finally, we build a test set for the evaluation of the proposed methods. Okay, so first let's look at the translation errors in dialogue translation. So we found 3 major translation errors that frequently occur in dialogue translation, in Chinese to English dialogue translation. The first one is pronoun dropping, that because Chinese ProDrop language, like this example. So this is a big problem for Chinese to English translation. And second one is a punctuation dropping. Sometimes if you in the social network and chat with some people, many people just omit these punctuations. So this is also a challenge for a problem for the dialogue translation. The last one is typo. For Chinese, it means we use the homophones to replace the correct words as due to the pinyin import methods. So here, like this one. So this is the 3 main translation issues we found in dialogue translation. And here is the statistic about these 3 translation issues. Okay, so how do we build a dialogue translation model? Because we don't have a lot of dialogue translation training data, and also found a big difference between training and the inference, because in the training we only have the clean sentence label pairs, but we for the test we have noisy dialogue label pairs with these translation errors, with these translation problems. So we actually use some automatic methods to generate pseudo training data to mimic this translation problem in dialogue translation. So with 2 steps, first step is try to obtain the sub-document from the dialogue corpus. And the second step, we generate some contextual perturbations into these sub-documents to mimic this translation problem we found in dialogue translation. Okay, so let's look at the first example. This is actually is a simple step that we just try to extract a sub-document pairs from the dialogue translation data from both the source side and the target side. And each sub-document contain utterances, and then we concatenate these utterances into one sequence and separated by this simple sepal. Okay, so in the second step, we inject some perturbations into this extracted sub-documents with 3 kind of translation problems, like PunDrop, ProDrop, and DialTypo. These 3 kind of issues. So for the PunDrop and the ProDrop, we just remove these pronouns and the punctuations with a probability of 30%. And for the DialType problem, we actually choose a word with a probability of 1%. And for these chosen words, we replace them with one of their homophones with 80% and with a random word with 20%. So in this way, we create a pseudo training dialogue translation data, and this data includes these translation problems in the dialogue translation. Okay, since we model this problem in a multitask learning way, we try to teach the model to predict this kind of errors. So we also attach the labels to the sequences, like we use the 0 to tag the correct words, and 1 for the DialTypo, and 2 for the ProDrop, and 3 for the PunDrop. Okay, so once we have this training data, we build 3 dialogue translation models, and the first 2 are serve as the baselines to compare our proposal. So this one is the repair dialogue translation model. In this model, we actually use 2 sequence-to-sequence model. The first sequence to sequence model, try to convert a noisy import to a clean import. Then in the second one, we use the transformer encoder decoder to translate this clean import into the target language. So this is the first model. In the second model, we use the build a robust dialogue translation model. In this way, we just combine our clean data and the noisy data together to train a robust dialogue translation model. Okay, so this is our proposal. MTL dialogue is a dialogue translation model in the multitask learning framework. Also use the context. So in this framework, actually is also not difficult. So in first, we use the encoder decoder to translate the noisy import to the target language, but in the same time, we also try to predict its labels of the import the noisy data. I mean, the labels as the 1 from 0 to 3 that we mentioned before. So this is this first task, the contextual labeling task. Actually, it's a sequence labeling task. We can use the BERT or something other models to perform this task. So this is the sequence labeling loss here. We actually use both the clean data and the noisy data. So we have 2 losses for the clean data, 1 for the clean data and 1 for the noisy data. And so we have the translation loss and sequence enabling loss. We combine these two losses together with a lambda here. The lambda is dynamically updated during the training. Okay, so since we don't have a test set to evaluate the dialogue translation model, so we build a Chinese English test set. And this test set actually contains these translation issues. And here shows the statistics of this test set. And to evaluate these three issues for the PunDrop and DialTypo, we use blue score to evaluate them. And for the ProDrop, we use accuracy, a kind of a percentage of correctly recovering and translating in the dropped pronouns. Okay, so we evaluate our methods in baseline and proposals in two modes. One is offline mode, and the other one is online mode. In the offline mode, we actually have the entire dialogue available. So we just concatenate all utterances in the dialogue into one sequence and then import this concatenated sequence into the translation engine. In the second one is the online. That means we actually try to mimic the actual chatting scenario. We continuously getting new source utterances. So that means we can only have the preceding previous translated sentences as the context. We don't have the succeeding context for our dialogue translation. So that's the basic difference between the offline model and the online mode. Okay, so let's look at the results of offline setting. So we compare our proposal with these two baselines, and we also want to know the oracle results for our model. So we use the gold plus place. This one is actually we import correct imports to the baseline model to see how to see the performance of this clean data. And so from this table, we can see here that the DialTypo actually has a very obvious impact on blue. We can see here the blue score has dropped a lot from the compare the clean import. And the recovery ProDrop actually is kind of really difficult, because we can see that in the oracle results we can correctly recover the dropped pronouns in 97%, but in our proposals we can only recover less than 50%. And here the PunDrop actually is a relatively easy issue to be solved. You can see from the blue scores that's compared with the oracle results, just only 0.3 blue drop here. Okay, so let's look at the online setting. Just as I mentioned before, the only difference between the offline and the online setting is that in the online setting, we don't have the succeeding context to be used for translation model. So we can see here the ProDrop actually in this the performance dropped a lot. So this means that for this issue, the succeeding context is very important. Okay, so that basically for the second work conclusions. We find three main issues in dialogue translation, and we propose a multitask learning framework to, to combine the translation task and the sequence labeling task to improve the translation quality. And we can see the context is actually very important in dialogue translation, especially for the ProDrop translation issue. So that's all. That's my talk here.
Thank you very much, Deyi. I'm always really impressed by how you manage to improve the performance of your models. That's something I've always struggled with. Have you got any questions from the audience today? Yeah.
Yeah, so I have a question. So thanks for your great talk. It's very interesting. And I have a question. Maybe I lost something during your talk. So in the first part, you said that you are modeling these cohesion devices. So I'm wondering that how did you annotated these cohesion devices or generated automatically?
That's a great question. Maybe actually, we use external resources like the water lake and the kind of policy tiger to detect these cohesion devices. So that's when we annotate these cohesion devices. We actually, sorry, I can't, I don't include these slides in here.
Okay, thanks. I will check the paper. Thank you.
Yeah, so you are using an automatic parser to get the cohesion devices. Do you have an idea of like how much noise you get from that parser and to what extent that makes a difference for your model?
Yes, that's a good question. So, actually, these parsers are not perfect. They make a lot of errors. But in currently, we don't analyze this kind of errors on the, the impact of these errors on our performance. We just use these external resources to see how this can, if we model this cohesion device and see how they can improve our translation quality. But we, in our field work, we decide to, investigate this impact. We think this kind of, maybe we have a good parsers, we have a higher performance. In this way.
Yeah. Okay, we've got a couple of questions in the chat here. So one is from Beg Rant. Would you like to ask your question yourself, or should I read it out?
Sure, I can ask it myself.
Okay.
So I was basically wondering if the cohesion devices work is the same work that's published in 2013, or if there's more recent work on it.
Actually, this 2013, I'm not sure on mentioning the 2013 paper, but now actually we have have done some work in statistical machine translation that try to incorporate a cohesion device into SMT, but in NMT that's quite a different architecture from the SMT. So that's different way to incorporate these cohesion devices. So
yeah, because you had mentioned masked language modeling, but I couldn't find anything on your website that was a more recent paper. So I'm just wondering if there's something I can read.
Okay, this paper just accepted by Colin 2022.
Okay.
Okay, release our papers.
Oh, great. Okay, I will look forward to reading it then. Thank you.
Okay.
It's too new. Okay, we have another question from Vimal Kumar, who is asking whether cohesion devices can be helpful to handle free word order languages.
Actually, I'm not quite familiar from the free word order language, so here I cannot quite clearly answer these questions.
Okay. So one question that I wanted to ask is, if I understand this correctly, the cohesion device masking work that you presented is a language modeling task primarily. This is not a machine translation system. Is that correct?
Yes. You can see this is a kind of language modeling task, but we use the mask language model to, we mask the cohesion device and force the encoder to predict this mask token here. Maybe this figure can show this. We mask the cohesion device in the current sentence and force the encoder to predict this mask token. This kind of mask language modeling task.
So it's a monolingual task, right?
Yes, it's a mono.
Is that correct? Okay, I just
use
wasn't
the
sure.
encoder side. We didn't didn't do this in
Yeah.
the decoder side. Yeah.
Okay, but here you've also you're actually extending this to machine translation, because that's what I was going to ask about. Like, how would you go about putting this into an empty system? But I can see that you've already got this on your slide.
Maybe I go too quickly.
So I just have a
Yeah.
follow-up question regarding this prediction part, masking part. So here, like, I mean, from the figure, it seems that do you feed the representations of masks, mask tokens to the decoder, or like the predictions from the predictor to the decoder?
Yeah, that's a great question. Actually, in the training process, actually all these components are just use a training phase. So we mask this token and force the model to predict the mask token, and also the encoder will generate a translation. But we during the training phase, actually we have the oracle results for the target translation to guide the decoder to train the decoder, right? So during the inference phase, actually, we remove all these two components, because if we still mask the import tokens here, that's a big problem for the decoder, because we don't the decoder don't know which word to be translated, and we cannot trust the encoder to correctly predict these mask tokens. So we just remove these two components. But during training phase, we actually use these components to update the parameters of the encoder and the decoder. In this way, we teach them to how to use this context maybe they can focus on these Cohesion devices to generate targeted translations. Yeah.
Yeah, thanks for your answer.
So which Cohesion devices are the most important?
Here I don't have the results. Maybe on paper I'll have this result. I check later.
Oh, okay. Oh, okay. That's fine. Okay. Have we got any more questions from the audience? If not, thank you very much, Deyi, for your
Thank you.
great talk. Thank you so much.
Thank you for having me here.